Good evening. Let's start. We are going to start with our first demo lecture for CS1, that is Core Statistics 1. So okay. Our CS1 subject, that is our Core Statistics 1 subject, is the basic statistics till all the analytical statistics. So we are going to start from very basics of statistics and we are going to go till analytical statistics. So we are going to learn all the different tools that we'll need for this analysis on any kind of statistical data. Okay. Now this is the course that we are going to follow. Okay, so these are the topics. We have 16 chapters. We have data analysis, probability distribution, generating function, joint distribution. Okay, so we are going to follow all these 16 chapters, but before that we are going to go through some basic chapters as well. Okay, so the basic chapters that we are going to study. So these are the three chapters that we are going to go through: data summary, probability and random variables. These are going to be very important for us to follow through the CS1 course. Throughout the lecture, if you have any doubts, you can unmute yourself and ask me the doubts, or you can type it in the chat. I have the chat open as well. Okay. Today we are going to see the basic chapter 2, that is probability. Okay. Now before we start that, I want to ask you a question. What is statistics? I would like all of you to answer. You can unmute and speak, or you can type it in the chat. Both will be fine. So anything, whatever comes to your mind whenever we say statistics. I would like our classes to be interactive, so I would like you to answer as well. So what is statistics? What comes to your mind whenever you hear the word statistics?
So about data, like collecting it and then interpreting data.
Okay, good. Collecting and interpreting data. Okay. Then data organization and analysis. Good. Anyone else? These are good points. So yes, statistic does apply on data. So we'll be working with data and we are going to collect data. We are going to interpret, organize, all of them are correct, and then we are going to analyze. Right. So these are good points. Yes, one more thing that we do is we do predict. So we are going to collect data, we are going to interpret, organize, then analyze it, and after that we are going to predict what might happen by using the data that we have collected in the past. So this is statistics in a nutshell. Okay, but this does not tell us what statistic is. This is what we are going to do in statistics. So what we are going to do in statistics, yes, all of that is covered here. Okay, but what is statistics? Okay. I always say statistics is nothing but a tool, very similar to a hammer. A hammer can be used to create a table or it can be used to destroy a table. Similarly, statistic is nothing but a tool. It is used for analyzing stuff and predicting the future. So you are constructing something called as models out of a statistics. So what we do is we construct models that can be used for, we'll not be collecting data with the models, but let's say interpreting, organizing, analyzing and predicting the future. These are the different stuff you can do with a model. Model is nothing but simply like a machine. You input something and you get output out of it. So your outputs are going to be some form of either analysis or some kind of a prediction or maybe organized table or something like that. Okay, that would be your output. And your input is going to be data. So you input data and you get output of either predicted values or analytical values or maybe organized data, whatever. These all could be your outputs. Okay. So model is working like a machine. Now the problem with statistical model is, the reason I call it as a tool is because we cannot predict future perfectly. Nobody can predict future. If somebody can predict future, then that person would become rich, right, beyond measures. So we cannot predict future. What we are trying to do is make informed decisions. We try to make informed decisions. Like today there is a cricket match between India versus Bangladesh. Now let's say you have never heard about what cricket is. If that is the case, I tell you, or if I ask you to predict who is going to win, you will say, I don't even know how cricket is played, I don't even know which team is playing, I have no idea about it, right? But still, if I say, just predict, will team A win or will team B win? So let's say team A is India and team B is Bangladesh. Okay, so for you, it's, you have no information about it. You might just choose A or you might choose B, and there is a 50% chance that you are correct because there are only two choices, right? But somebody who knows cricket, okay, would say maybe India is going to win, because India is a better team than Bangladesh. It's been winning in past few years or something like that. Okay, and somebody who follows cricket a lot, who watches cricket a lot, will say the Indian team that is playing right now is in form, so there is a very good chance that India is going to win. Right? So the more you know, the better your prediction is going to be. You might say this player A is going to play well, that player B is going to take these many wickets, player C is going to do this and that. Because you might be following that cricket, more closely. So what is happening is, the more information you have, the better prediction you might be able to make. Again, you cannot be 100% correct. It's not possible. But the more you know, the better your decisions will be. Now, if I say bet that Virat Kohli is going to, make a century. Okay. So somebody who does not know anything about cricket would, bet on it. Somebody who knows cricket, who has been watching cricket recently, would say that Virat Kohli is not going to play in today's match. Right. So the better you are informed, the better decisions you are going to make. Right. So what we are trying to do is, we are going to make informed decisions. Okay. So the better information you have, the better prediction you can make, and there is more chance that you will be able to predict something in the future. So when I say better chance, what does that mean? What does a chance mean? When I say there is a better chance that you will be able to predict the future, what does chance mean? The other words that we use is likelihood. There is more likelihood that you will be able to predict, or we say probability. We use the word chance or likelihood or probability. Okay. So whenever I am saying there is a better chance that you will be able to predict the future, that just means I am calculating the probability. You are more likely to succeed rather than fail. So when I say more likely, I am talking about probability. So if I say probability of succeeding is more than 50% or 0.5, then you have a better chance of succeeding than failure. So what we are doing is, we are calculating probability. Whenever we say chance, whenever we say likelihood, we are meaning nothing but probability. So statistics is just a tool that helps us to predict. It can be used in science, it can be used in commerce, it can be used in arts. That is why we don't categorize them, statistics in science, commerce or arts. It's just a tool that will help us analyze in every field. So just as any tool, you can use it properly and create, amazing models that will give you very good predictions. Or you can use it to destroy your predictions, right? So if your models are not correct, if your statistics is not correct, you will get wrong answers. Okay. So this is very important for us to understand not only the tools that we are using, but how should we use those tools. So throughout this course, we are going to study how statistics is used and how it should not be used. Both of these things we are going to study throughout. Chalo, let's start with probability. So when I say probability, it is nothing but, okay, before we start probability, let's talk about sets. I hope everybody has studied sets. Everybody has studied sets before. I'll give you a brief idea.
No, I don't know about sets.
Okay, so you will have to go through a little bit of sets in your +2 course, but I will give you a brief idea about what sets is. Okay.
Okay.
So a set is represented by a capital letter, and we say it is nothing but collection of similar items. So when I say collection of similar items, similar words, similar whatever, everything can be part of a set. So we say elements. So these are elements. So let's say I am saying set A contains 3 elements A, B and C. Similarly, if I say set B contains, it is represented by these curly brackets, let's say B, C and D. So what happens is, we say any element in the whole universe is only going to be there once. That means this B and C occurs only once in the universe. So if it is part of set A and it is part of set B, they must be the same elements. Okay. So a set can contain elements from other set as well. So what we can do is we can unite those sets, or we can say find the union of sets. Union, we write it as A, B. This is not a U, this is a sign, symbol like this. Okay, it's not a U, it's a sign for union. And in union, we say we are going to combine both those sets. So I'll be write it as, so you will see that the union does not contain B and C 2 times, because B and C only exists there once in the universe. So when I combine A and B, they are combining both B and C and having it only once. Okay, we can represent a set using a Venn diagram. In a Venn diagram, we first draw a box. We call it as the universal set. It contains everything. Universal set can be represented by X, U, S, whatever. Okay, there are many ways of representing a universal set. I am just naming it as X. It contains everything. It's the whole universe. And let's say, I'll color code. Let's say this is A. It is represented by a circle. And this is B, represented by another circle. So here I would say that my elements, A is part of this portion, D is part of this portion, and B and C are common to both A and B. So it must lie in this common region between A and B. This is how I will represent these sets. Okay, so when we draw a Venn diagram, we say that the area under this circle is going to represent the whole set. Okay, so this region where we have B and C will have something in common between A and B, and we call it as intersection. Intersection is nothing but whatever is common between A and B. So I'll say A, this is the symbol for intersection. B, A intersection B will be nothing but B comma C. These are the elements that are going to be inside the intersection of A and B. Okay. Then we have complement. Complement of a set can be represented as A bar or AC or A dash. Any one of these are fine. Okay, you can represent complement with any one of these symbols. And a complement just means everything other than that set A. So when I say A complement, I mean everything other than A. So it will be the whole universal set minus whatever is in A, that comes into everything other than A. So if let's say my universal set X contains . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Let's say my universal set contains A, B, C, D, E, F. Okay. So if my universal set contains A, B, C, D, E, F, but A union B contains only A, B, C, D, then E, F must be outside A and B. Okay, it is part of the universe, but it is not part of A and B. So in such case, if I say A complement, it means everything other than A. It will contain everything but not this A. I'll have to remove everything that is part of A. So A, B, C would not come in intersection, in complement, and I will have D, E, F. This will be the complement of A. Okay. We say that A union its complement, or let's say A plus its complement, should make up the whole universal set. If I add up A and its complement, it should make up the whole universal set. Okay. Now we are usually not concerned with what are the elements in a set or such things. What we find is number of elements in a set. Let's say number of elements in set A would be denoted as NA. Okay. So accordingly here, if I say number of elements in A were 3, number of elements in B were also 3, number of elements in universal set were 6. Okay. In union, I had number of elements in A union B as 4, number of elements in A intersection B were 2. So for us, counting the number of elements is more important rather than writing down all the elements. So we make some formulas using this number of elements. We say that the number of elements in A union B is same as number of elements in A plus number of elements in B minus number of elements in A intersection B. You can see that here. Okay. I have 3 plus 3 minus 2 gives me 4. Right. Union is nothing but everything A as well as B. So this whole thing will be nothing but union of A and B. And this is going to be the intersection, that is the common region between A and B. Okay. So I can write union in another way. I can say that I have only A part, that is this one. I can have only B part, that is this one, and then I can add up the intersection. So I can write union in another way. I can say number of elements in A union B would be number of elements in only A plus number of elements in only B plus number of elements in A intersection B. Right. So how do I define this only A, this portion? So you can see it is A, but it does not have B in it. Anything that is contained in B is not part of it. Okay, so the way we can write it is number of elements in A, but means and. See, one more thing. Union is similar to or. So you can write it as or, and intersection is similar to and. So whenever we are going to convert anything into language, whenever I say a element is in A or in B. So that represents nothing but the union, because it is an element that is in A, either A or in B. And similarly, whenever we are talking about intersection, we are usually using the word and. So we'll say an element is in A and in B. That tells us that it is in the intersection of A and B. So whenever we are constructing something from language, from logic, then we'll see these words or and. And everything that goes with or, neither nor, either or, you will find that it is nothing but going to translate into union. Whereas and, but, or similar stuff, whatever, I don't remember much, these all will make intersections. So similarly here, when I say only A, I can call this as A but not B. Any element that is in A but it is not in B. So when I say but, it will be an intersection. Not B will be nothing but a complement. B complement. So again, complement of a set, I can call it as not A, right? Complement of a set A, I'll call it as it's not A. So this is nothing but A but not B. Similarly, only B can be written as not A but B. Okay, I prefer to write sets in one single order, that would be alphabetical order. You can always write B intersection A, that is same as A intersection B. The order of the sets will not matter. Similarly for union, the order of the sets will not matter. Okay, so I prefer writing them in the alphabetical order, it's just easier. And then plus I will have A intersection B. Okay, this is another way of writing the same thing, that is A union B. Okay, so you can do the counting here. When I say only A, that contains only one element. Only B contains only one element. So N A intersection B complement will be 1, and A complement intersection B will also be 1, and intersection has 2, so you can add them up. 1 plus 1 plus 2 will give you 4, right? That makes up the union. Now we can extend this to 3 sets. Let's say I have 3 sets. Let's say I have A, B, and C. I have 3 sets A, B, and C. So if I want to find number of elements in A union B union C, then we can write it as number of elements in A plus number of elements in B plus number of elements in C. Now if I add up A, B and C, there are certain common regions that are going to be added twice. So this region is common to A and B both. So that has been added 2 times. I need to remove it once. So I'll remove it. I'll say that is nothing but number of elements in A intersection B. Okay. Then similarly, this region has been added twice. That is B intersection C. I need to remove it. Number of elements in B intersection C. Similarly, this region has been added twice. So that is Number of elements in A intersection C. Now what is happening is this small region that is called as a triple intersection, all three are intersecting at that point, had been added 3 times in A, B and C, and have been subtracted 3 times in A intersection B, B intersection C and A intersection C. So added 3 times, subtracted 3 times, we don't have that, so we'll remove them. So we will add them again. A intersection B intersection C. This is how we make this formula. Okay, this is how we make the triple 3 set union formula. Does that make sense? Okay. So there are a lot of formulas that we make in sets. Okay. We are going to only go through a few of them, not all of them. Okay. But here I want you to make another A union B union C by adding up all the bits and pieces. So if I say this whole region, that is only A. This part is, let's say, only A. It does not contain any B, it does not contain any C. Plus, if I add up this region is going to be only B. Does not contain any A, does not contain any C. This region is only C. Similarly, this region is going to be A and B but not C. So if I represent this with small a, small b, small c, this is, let's say, small d, e, f, and this is g. So if I add up all of these regions, I am going to get A union B union C. Right. So this small a is nothing but only A. So I'll add up only A, only B, only C. Then I'll add up A and B but not C. Instead of writing not C, I'll write C complement. A and B but not C. Similarly, that is this D. Okay, that is A and B but not C. I can add up. Next is B and C but not A. That would be this region. Then A and C but not B. That is this region. Then of course lastly I will have the triple intersection. That is this G. Correct. Now can you tell me how would we write only A? How would we represent only A in terms of intersections? Anyone? We did that here, right? We said only A is A but not B, right? We said it is A but not B. Here when I say only A, we have 3 elements, so I will say it is A, but not B, not C. A, but not B, not C. Similarly, when I say only B, it will be number of elements in not A, intersection B, not C. It is in B, but it is not in A, not in C. Similarly, not A, intersection not B, intersection C. These are only A, only B, only C. And this is the very clear A and but not C, A and B but not C. So it is A and B, but is also an intersection, not C. Similarly, not A, B and C. A, not B, but C. And lastly, triple intersection. Okay. Any problem here? So these are the different ways. This is one formula, this is the other formula for again A union B union C. There are certain other formulas. We can say A union B, the whole complement is nothing but A complement intersection B complement. Similarly, A intersection B, the whole complement is nothing but A complement union B complement. Okay. And there will be a few more. If I remember, I'll go on telling you. Okay, but these are the basics of sets that we'll require. Okay. Now we are not actually studying sets, we are studying probability. So we say probability is nothing but desired outcomes upon total outcomes. Okay, desired outcomes upon total outcomes, that is what we call it as probability. Okay. So we say that instead of sets we will have here events. Okay. So A, we'll call it as an event with certain outcomes. Let's say A is represented with A, B, C. So this is an event that is going to occur or that is occurring, and there are 3 outcomes of that event. So you can see the similarity. This is represented very similar to a set. And I'll say probability of A, probability that A would occur is nothing but number of outcomes in the event A upon number of outcomes in the universal set. Okay. This number of outcomes in event A upon number of outcomes in universal set. So we are going to use this, all of these formulas, and convert them into probability. So the first one that we studied, A union B, is number of elements in A plus number of elements in B minus number of elements in A intersection B. So now we can convert this into probability by dividing by number of elements in the universal set, or you can call it as total outcomes. So if I divide here, I'll divide on the other side as well. And that becomes nothing but probability. So this is nothing but probability of A union B will be equal to probability of A plus probability of B minus probability of A intersection B. So you can see that directly a formula of number of elements can be directly converted into a formula of probability. So even the formulas that we have studied, these three, can be converted directly into probability. Okay. Just a few restrictions. First would be that probability of the universal set is always going to be equal to 1, because it is going to be n of x upon n of x. It will always be equal to 1. And probability of any event will always be between 0 and 1. You can say less than, equal to, less than. Probability of any event should always be between 0 and 1. The maximum probability is going to be 1. That is of the universal set. So you can also calculate probability of a complement. It is going to be probability of the, remember we said that A plus A complement makes the universal set. I can say A complement is nothing but universal set minus the set A, and that would give me probability of A complement is equal to probability of the universal set minus probability of A. Probability of universal set is 1. That is 1 minus probability of A. This is another thing that we can use. Probability of complements. Now let me just take a question. Okay. So in a deck of 52 cards, one card is randomly selected. Find the probability that first it was a 7. Can you tell me what should be the probability that it was a 7? What are the chances that it was a 7? Anyone? So we'll say in universal set there are 52 cards. In our universal set there are 52 cards. If I assume that A is nothing but card was a 7. This is the event. This is the event. The selected card was a 7. So then number of cards that are going to be 7 are 4. Right? So we'll say probability of card being 7 will just be 4 by 52 or 1 by 13. For these questions I will just keep 4 by 52. It will be easier because denominators will be same. It will be just easier for us to calculate stuff. This is my first. Second, it was a club. Let's assume the event B is nothing but card was a club. Now I have in total 13 clubs in a deck of cards. So probability of B will just be 13 by 52 or 1 by 4. Again I'll leave it as 13 by 52. And third, it was a 7 of clubs. Now can you tell me how should I represent 7 of clubs using this A and B? How should I represent 7 of clubs using the sets that we have just learned? Anyone? So 7 of clubs, that means it is 7 and it is a club. So it's an and. So we'll say it is probability A intersection B. A intersection B, because it is 7 and a club, right? So it is A intersection B, and we have only one such card that is 7 and a club out of those 52. So we'll have 1 by 52 for the intersection. Okay. Now here it was a 7, either a 7 or a club. When I say or, it is nothing but A union B. Right. It is A union B, either 7 or a club. It would be A union B. That would be probability of A plus probability of B minus probability of A intersection B that is 4 by 52 plus 13 by 52 minus 1 by 52. We'll have 16 by 52. Right? Because there are 16 such cards. We have 13 clubs and we have 7 4 sevens, right? We have 13 clubs and we have 4 sevens, but one of them is common. So in those 13 clubs, I'll have additional 3 sevens. I have in total 16 cards that could be a 7 or a club. So that is why 16 by 52. So when we are going to study probability, we are going to say that there is an event with certain outcomes. Now, how likely is that event to occur? That is nothing but the probability of that event. Okay. Now, right now I want to give you a little bit of time, okay, before we continue anything here. I want you to ask me any questions relating to exams, relating to actual science if you want. I just wanted to give you a brief idea about what we are studying. If we require next 45 minutes, 1 hour, so we'll continue this study tomorrow. Okay, that's not a big problem. So let me know anything you want to know about actuarial science, the institutes, anything. You can ask me any question. Or should I just continue? So I'll continue. If you feel like, you can ask me anything. Okay. I will talk about mutually exclusive events. Now, if there is no outcome in common between two events, then they are known as mutually exclusive events. No outcome in common, that means we are talking about intersection. So we are saying probability that A intersection B will be equal to 0 because there is no outcome in common. That is what we'll call it as mutually exclusive events. Then mutually exhaustive events. So if two events together complete all possible outcomes, then they are known as mutually exhaustive events. That means together they should make up everything in the universe or the whole universal set. So A union B must be equal to 1. That is what a mutually exhaustive events would be. Here if I take this example of A and B, right? A is card was 7, B is card was club. So can you tell me, are they mutually exclusive? Are they mutually exclusive? A was that card is 7, B card is club. They are not mutually exclusive because they do have something in common. That is why we had intersection. Intersection was not 0, so they are not mutually exclusive. If I had something like diamonds and clubs, if I would have said that C is card is diamond, okay, so then B and C are going to be mutually exclusive because clubs and diamonds will not have anything in common. So then they become mutually exclusive events. Then mutually exhaustive, they should together make up everything. Now even if I add up all A, B and C, they are not going to make up everything. So they are not mutually exhaustive. They are not taking all the 52 cards into consideration. But if I say that, let's say event R is card is red, and let's say B is a card is black. So we know in the deck of 52 cards we have 26 red cards and 26 black cards, right? So together they make up the whole deck. So they are mutually exclusive because there is no such card that is going to be red as well as black. So they are mutually exclusive and they are also mutually exhaustive because together they make up everything. Okay. So together I'll have probability R, red card will be 26 by 52. B will also be 26 by 52 and intersection will be 0 because there is no card that is red as well as black, so 0. So you will have probability A union B, or sorry, R union B is 26 by 52 plus 26 by 52 plus 0, so that is basically 52 by 52 and the probability would be 1. So they are mutually exhaustive because there is nothing in common between them, and they are mutually exclusive because there is nothing in common between them, and they are mutually exhaustive because together they make up the whole universal set. Okay. Next term is independent events. So if the occurrence or the non-occurrence of an event does not affect the occurrence or non-occurrence of another event, then they are said to be independent. So let's say two events are independent. So if I say if A and B are independent, then we say probability of A intersection B will be equal to probability of A into probability of B. Now when I say occurrence and non-occurrence of an event does not affect the occurrence or the non-occurrence of another event, we are usually talking about their probabilities. So I am saying probability that A and B occur together. This is A and B occur together. That is why intersection. Okay. So because they are independent, they are not affecting each other. A does not care whether B occurs or not. B does not care whether A occurs or not. So they are independently occurring and we are multiplying their probabilities. Okay. So A is not affecting B. So occurrence of A does not affect occurrence of B. So similarly, occurrence of A does not affect non-occurrence of B. When I say A intersection not B, that means A occurred but B did not occur. So independent, that means occurrence of A does not affect non-occurrence of B, or non-occurrence of A does not affect the occurrence of B, or the last one, non-occurrence of A does not affect non-occurrence of B. They are independently occurring or not occurring. Okay, so probability of two things happening together, if they are independent, is just they independently occur, right? And whenever two things are happening together independently, we multiply their probabilities. So if A and B are independent, then all of these conditions will be true. I'll take an example. Let's say 3 cards. So in a deck of 52 cards, 3 cards are randomly chosen. Find the probability that all 3 are aces if each card is replaced before selecting the next card, or second is that cards are not replaced before selecting the next card. So in the first one, we have replacement. That means from that deck of 52 cards, we are randomly selecting the first card. We are seeing what that card is, and then we are replacing it back in the deck before selecting the next card. Then we are, let's say, reshuffling the cards, then selecting the next card, seeing what that is, then putting it back into the card, reshuffling it, then selecting the third card. This is how we are doing it in the part 1, that is replacement. We are replacing each cards after looking at what they are. Okay, replacing it back into the deck. Now what happens is, if I want to calculate probability that card 1 is ace, if I say card 1 is an ace. So in the deck there are 4 aces. So I'll say there are 4 by 52 chance that my card 1 is an ace. Similarly, because I have put that card back after looking at the card, whether it is ace, whether it is not ace, that does not matter. But I look at that card, what that card is, and then put that back in the deck. Reshuffled it. So I still have 52 cards, still 4 aces in the deck when I'm selecting the second card. So probability that card 2 is ace is also 4 by 52. Again, I selected the second card. I saw it. Does not matter whether it is ace or whether it is not an ace. I replaced it back into the deck, shuffled it before I selected the third card. So probability of card 3 being an ace is also 4 by 52. So whenever we have replacement, this just means they are independent. Because whether the first card was an ace or not did not affect the probability of second card being an ace. And second card being ace or not does not affect the probability of third card being ace. So they are not affecting each other's probabilities. They are each other's outcomes. And that is why they are independent of each other. So if I want probability that card 1 is ace, intersection card 2 is ace, intersection card 3 is ace, that will be nothing but 4 by 52 into 4 by 52 into 4 by 52. This is our probability. Now in our examination, we use scientific calculators. Okay, so throughout this course I am going to teach you how we are going to use scientific calculators. Okay, using this app. Okay, you should have a physical calculator. Now the physical calculator that you are going to buy, if you are giving examination from IAI, that is the Indian Institute, then you should buy Casio FX 82 ES Plus. This is the calculator that you are going to buy if you are giving the paper from IAI. If you are giving the paper from IFOA, then you should buy Casio FX 991 ES plus. Okay. These are the scientific calculators that we are going to use. Okay. Now they are very similar in functionalities. The 991 has more functionality than 82, but throughout what we are learning, there is nothing that we are going to not learn, or everything that we are going to do will be possible in both of these calculators. Make sure in both of them you are buying the ES version, not the MS version. They also have an MS version. Do not buy the MS version. There are certain functionalities that are present in ES version, not present in MS version. So please make sure while you are buying the ES versions. You can find them in most of the stationery shops, big stationery shops, or you can also order them online, Amazon, Flipkart, everywhere these are available. I'll show you. This is how the calculators look. Okay, these are the new versions. These are called as I think version 2 or something like that. That is fine. This is how the calculator look. These are the old versions. This is how the old calculator used to look. Any of them is fine because they have just changed the look of the calculator. The functionality has not changed. So either this or this, both these calculators are fine. Okay. So you can see I've just searched Casio FX 991 ES. Similarly, you can search 82 ES. And you can see that 82 ES also looks almost the same. Just the functionalities are different. The look is exactly same. This is how the old version looked. Color was different from the 991. But here they are not even changed the colors. I think these all are available in multiple colors. There's pink available, gray available, blue available. Does not matter. These are just aesthetics. So okay, this is how the calculators look. Okay, and for us, you can see this. Okay, it's available online. If you see this calculator, it's very important that you see that there are a lot of buttons. I'll show you using the app. So you will have multiple sections of the calculator. You can see down here you have the numbers and plus, minus, multiplication, division. That's very straightforward. But above that you have certain buttons. Okay, these let you do more functionality than just basic calculations. And above that, in that diamond pattern, you will see 4 buttons here in the diamond pattern. It's just a little bit better visible in the old version of the calculator. So this is the old version. I just want to show you. Okay, the layout is almost the same. Okay, this is the old version. You will see that here, top here in this circle, we have 4 buttons. They are called as navigation keys. Okay, so these are the navigation keys. Here, if you look, these are the navigation keys in the center. Okay, so anyways, as we go along, I'll teach you how to use the calculator. Okay, using this app. Okay, so of course you should buy the physical calculator as soon as possible. The more you practice, the faster you will become in that calculator. So throughout your course, you should practicing with the physical calculator and not with any app on your phone or something. Okay, but by any chance, if you're downloading an app, make sure that it has these navigation keys in here, you can see. So I just searched scientific calculators and I found one with these 4 navigation keys. This is going to be important. The layout of this is almost the same as the physical calculator. That is why I have taken this. Okay. So what happens is, you can make very detailed equations here in this calculator. As we go along, I will be teaching you how to make the equations. Like here, I wanted 4 by 52 into 4 by 52 into 4 by 52, right? Or you can say 4 by 52 cube. So instead of writing 4 divided by 52 and then multiplying by 4 divided by 52, we can make the fractions. You will see here there is a fraction button here, right? See here. So I can put a bracket, I can put a fraction and say 4 by 52, bracket close. Okay. And then I want raised to 3 because I want cube. So for raised to 3, I have this button here. You can see x raised to box. I can do x square directly, or I can put x raised to box and put any power. So when I press this, I'll get a power and I'll put 3. Now if you observe, the cursor is on the power. So if I had more things to write in the equation, let's say I wanted to add 0.5 or something like that to this. So if I just add here plus 0.5, you can see everything is going into the power. So I can make an equation even in that power as well, but I don't want that. If I don't want that, I need to come down of that power, so I'll use the navigation keys here. So if I press the side arrow key, you can see that the cursor is now here. So now I can do plus 0.5. But I don't want to do that. This is all I wanted. So equal to, and I get the answer here. Now in your physical calculator, you will find that the answer is given in terms of fractions. Okay. This is how the answer would be given. 1 by 2197. If you want to convert your answer into decimal, there is this key SD above your del. You can see here SD. You press that button, your fraction will convert into decimal. You press it again, it converts back into fraction. So this button converts your answer from decimal to fraction, fraction to decimal. Okay, so depending on what do you need, you will use that. Okay, so as we go along, I will be teaching you different things, different functionalities of this calculator. Okay. Right now let's keep it aside. Let's go to the second part. Okay. In the second part, we are saying cards are not replaced before selecting the next card. So without replacement. Now if the cards are selected without replacement, that means we saw the first card and without keeping it back inside the deck, we selected the second card and then we selected the third card. You might say we are selecting 3 cards without putting back the first card in. So that would be without replacement. So in that, what happens is, in the first card, I may have 2 outcomes. Let's say I got an ace or I did not get an ace. I'm saying ace is A and not an ace is N. Then in the second card, I may have got another ace or not an ace. So in first card, if I got an ace, then I would have an ace, not an ace. Similarly here, ace, not an ace. This is the second card selection. In the third card selection, again I could have got an ace, not an ace. Now what I have done here is made a tree diagram. Why? I'll tell you right now, because in the first card, let's say I got an ace. I'm not replacing it back into the deck. So what happens is, probability of getting an ace in the first card is 4 by 52. We know that because we have 4 aces and out of total 52 cards. But now when I'm saying I'm selecting a second ace without replacing the first, now the total cards in the deck are going to be 51 because I took that ace, kept it aside. So in the deck now I have only 51 cards, and that too, out of those 51 cards, only 3 of them are going to be aces because one of the ace is already out of the deck. So now the probability that I will get another ace is 3 by 51. Now imagine the first card was not an ace. If the first card was not an ace, I got an N. In that case, I had probability of 48 by 52 because I had 48 cards that were not ace. So probability that I will get not an ace would be 48 by 52. But now again, that not an ace is outside the deck. So in total I have only 51 cards, but out of those 51 cards, 4 of them are aces. So probability that I will get an ace after I have got not an ace in the first card would be 4 by 52. Does that make sense? Right? So irrespective of whether we got an ace or whether we did not get an ace in the first card, probability of getting an ace in the second card is not same as probability of getting an ace in the first card. It was 4 by 52. The denominator definitely changed. Irrespective of whether we got an ace or we did not get an ace, in the first card, probability of getting an ace has changed in the second card. So they are not independent of each other. So when I say without replacement, I'm saying they are not independent. So to find the probability when we have not independent cases, what we can do is we can make this tree diagram. I can figure out the other branches. I can say if I got an ace in the first card, I will have 48 not aces still left in the card, still left in the deck out of 51 cards in the second selection. Right. I will have 48 by 51 probability of selecting not an ace in the second card. But in the first card, if I got a not an ace, and now I am trying to find probability of getting not an ace in the second card, I will have only 47 cards that are not aces out of 51 cards that are not aces. Similarly, I can do the others. I will say probability of getting ace in the third card when first two are aces. Okay, first two are aces. So I'll have 2 by 50. Here I'll have 48 by 50. This I got an ace, then not an ace. So for this I'll have 3 by 50. 47 by 50. Here N and then A. So 3 by 50. 47 by 50. Here N, N. So 4 by 50 and 46 by 50. these will be the probabilities, and if I want to find probability of getting all 3 aces, I'll have to multiply all of these 3 branches. Okay. So the possibilities of cards that I can get is A. I'll write it here, or AAN, ANA, ANN, NAA, NAN, these are all the possibilities of selecting 3 cards. Okay. And probability of getting all 3 aces would be 4 by 52. Okay, so I can say probability of getting card 1 as ace and card 2 as ace and card 3 as ace will be equal to okay, ये 3 will multiply these 3. Okay, so we'll have 4 by 52 into 3 by 51 into 2 by 50. Okay. So here you can say 4 by 52. See, I am using the navigation keys so that I can get out of this fraction. If I press side arrow key, then multiply, and again a fraction 3, then I'll have to go down by 51, then side into fraction 2 by 50. So you can clearly see that the probabilities are completely different. So when they are independent versus when they are not independent, right? Now we can solve this using permutation and combination also. Is there anybody who has not studied permutation combination? If you have not studied permutation combination, and I have made videos on YouTube, okay, just on YouTube, if you just search 2 irrational, okay, 2 irrational, yeah, this is the one, 2 irrational, this 2 irrational you can see, and there are videos. I make a lot of videos related to actual science, you can go through them. But if you go to the playlist, no, not this playlist, playlist here, here, this is the playlist, okay, and in this playlist, you can see permutation combination. There are 3 videos. There are certain I've made certain videos on the basics of mathematics that you will require. You can go through that also. This is the one. So you can go through the playlist. You have permutation combinations, then you have differentiation, integration, vectors, matrices, trapezium rule, Newton-Raphson method. These are something that you can go through. These are some basics that we require throughout our course. Okay, you may have studied them, you can refresh them. Then if you just want to go through permutation combination, then that is it, no problem here. I have made calculator videos. Okay, so these are the calculator videos. Go through them. Okay, introduction, then how to solve single variable equation. You can do that later. Storing values is important, so introduction, storing values, these are important. Okay, throughout anyways I am going to teach you, so not a big deal. Just go through introduction if you want to right now. I'll be teaching you throughout whatever is required. Okay, so right now if you want to, you should go through only the introduction video of the calculators. And please make sure that you are prepared with the permutation combination tomorrow, because we are going to discuss that. Okay, sure. So let's end the class here. Tomorrow again we'll conduct the lecture 5 to 6:45 demo lecture. You can join in with the same link. Okay, bye.